How about now? There we go. I'm live again. Okay, so welcome back everybody to day 2 of Solar System Exploration to 50, our symposium co-sponsored by the National Air and Space Museum, the Science Mission Director at NASA headquarters, JPL, and of course the NASA History Office. We had, I think, a really interesting day yesterday, and we've got another interesting day ahead for you today. A little less overscheduled today than yesterday, so a little more time for people to chat and do some things. So I think you'll enjoy the day. And be sure to stick around for the afternoon panel. I think it's going to be a real interesting one, our closing panel. In case you forgot, I'm Bill Barry, NASA Chief Historian. And before we introduce our keynote speaker today, let me run over a couple of administrative announcements. For those of you who weren't here yesterday, the safety briefing is if something happens and we need to exit the building, exit the doors to your left over here unless you're told otherwise, and they'll get you outside. For our courtesy announcement for the day, remember to turn your cell phones to vibrate mode or some other quiet mode so we don't interrupt the speakers. Lunch today is on your own. So, and we have a tradition here at our NASA History Symposia that you always take a buddy to lunch. So don't go eat lunch on your own. Go find somebody, particularly somebody that you haven't ever talked to before or somebody that you want to develop an acquaintance with. Take them out to lunch and go have lunch together. So we'll have a break for lunch this afternoon for that. Again, we're doing a live webcast today, so welcome to everybody who's online. And for those of you here in the room, please remember that if you're going to ask a question, we do have the microphones in the aisleways there. Make sure you're on microphone when you're talking so that everybody on the web can get us. And also that it's appropriately archived because the webcast will be available in the future for people to watch, or if you want to come back and watch yourself again. Okay, again, my thanks to our host, Lockheed Martin, and to all the staff that's worked on this. If it was successful yesterday, it was largely a result of the work of a lot of people behind the scenes that you don't see, not i.e. not me. So I have great thanks for all those folks, and we'll make comments about that at the close of the day again today. But without further ado, let me introduce Linda Billings, who will kick off our keynote speakers by introducing them. Linda.
I'm pleased and honored to be able to introduce our morning keynote speakers, who I'm sure will wake us all up if we're not already awake, with a very interesting talk, which I've been anxiously awaiting to hear. I remember when I first met Wes Huntress, he had just left JPL for headquarters, and I had asked him if he would come and speak at a career day at the Thomas Jefferson High School for Science and Technology in Virginia. And I remember asking him, why the heck would anybody want to leave Southern California for here? But he stayed miraculously, and as we've heard yesterday, has accomplished a lot for the field of science. And he's currently chairing NASA's, the NASA Advisory Council's Science Advisory Committee. And I particularly admire Wes for taking a stand and stepping down at a time a few years in the past, and then coming back to take charge of that committee. And I just yesterday met academician Mikhail Marov, great pleasure. And I'm not going to read bios here, but academician Marov, you've heard about his accomplishments yesterday too, and we'll hear more today. He's a member of the Russian Academy of Sciences and the International Academy of Astronautics. And Wes has been very active in the International Academy of Astronautics, so I'm sure these two have done a lot through IAA over the years. And so as not to take up any of the time from the interesting story they have to tell, I'm going to let them come up to the podium.
Well, good morning, everybody, or Dobry Utro, if you happen to speak a little Russian. Let me make sure I know how this thing works first. Well, that one's not mine. Help from back there. No thanks. That way, aim it that way. No, you don't want to hear me sing. That would really wake you up. Okay, here we go. Well, what Mikhail and I would like to do this morning is to tell you a bit about the other robotic lunar and planetary exploration program, that of the Soviet Union, with an emphasis really on the early years during its formulation and development period between 1960 and 1975. You know, it was really born as part of the Cold War, just as our own was. And because most events in the Soviet program happened behind the Iron Curtain and were virtually unknown outside the closed circle of Soviet secrecy, other than their successes, it really provided a rather mysterious stimulus in the American program. But behind that wall, it was really a tale of adventure and of excitement, and also suspense, tragedy, a real dramatic program. And it also is a tale of great accomplishment alongside very debilitating losses, and driven really by a thirst for technological achievement, just as our own, and a desire for international recognition and respect. Now, in the early years of space exploration in both the U.S. and the Soviet Union, they were driven by strong personalities in those days. Men, singular men who were visionaries, superb engineers, and strong leaders. Now, in the U.S., of course, it was Wernher von Braun, and in the Soviet Union, it was this man, Sergei Pavlovich Korolev, the mysterious designer. His name was a state secret until he died. And he was, just like Werner, he was mostly interested in space exploration. But he could only get a job as a designer of military rockets. And he was the man who designed the Soviet Union's first ICBM, the R-7. And to influence the government to conduct space exploration with his rockets, he teamed up with the head of the Soviet Academy of Sciences, Mstislav Keldysh, who was a public face and who was known in the Soviet Union as the chief theoretician of the program. Well, the Soviet rockets were much more powerful than the U.S. rockets in the early days, and therefore they were a great boon for space exploration payloads, and Korolev made good advantage of that. The R-7 ICBM was first tested in April 1957, and Korolev had to fight the Army to get permission to use it during test flights to launch a satellite. We all know what the result of that was in October 1957. And then, in order to do lunar missions, he invented a three-stage version called the Luna. And then later, in order to go to the planets, he devised a four-stage version, which was called the Molniya. And that vehicle could throw 5 times the weight of the Atlas Agena. So it was a great advantage for him. It could throw about 1,600 kilograms to the moon and about up to 1,200 kilograms to Mars and Venus. And the R-7, as you all know, became the most successful space launcher in history, and today is known as the Soyuz for both manned and unmanned flights. Well, in 1958, the U.S. announced that it was going to launch a spacecraft to the moon. Korolev, of course, paid quite a bit of attention to that, and he decided to prepare a spacecraft, a lunar spacecraft, and that three-stage version of the launcher to beat the Americans. And during that fall of 1958, the Soviet Union and the U.S. traded 3 launch failures, and it was rather a dramatic contest on both sides. The Soviet Union was clearly aware of what the U.S. was doing. They knew the launch dates, and they were trying to blindside the Americans. The U.S. was groping blindly to try and seize the lead, but it was Korolev who was successful. The age of robotic, lunar, and planetary exploration began with the successful launch of Luna 1 on January the 2nd, 1959. Now, it was the first spacecraft to leave Earth's gravity field, first to fly by the moon, and the first to enter heliocentric orbit. But it missed its prime objective, which was to actually impact the moon. And so Luna 2 was the first to do that later in the year, on September 14th, 1959. And Luna 3 was the first to circumfly the moon and to photograph the far side. Luna 3 was also the first spacecraft with 3-axis attitude control, which it had to have in order to do the imaging. Well, bolstered by his lunar success, Korolev wanted to go to Mars and Venus next. And so to meet planetary launch windows in 1960, he needed to build the 4-stage version of the R-7 and a planetary spacecraft to go on top of it within 8 months, all of which he did. It's rather amazing, actually. So the first launch of the 4-stage Molniya carried a Mars spacecraft. But it was actually the first spacecraft with solar panels. You can see them there. Onboard propulsion, which is under the dome at the top of the spacecraft, and long-range communications. You can see the parabolic antenna. Unfortunately, both launches to Mars failed due to the launch vehicle. And 4 months later, Venera control problems. Now, in these 1960, 1961 launches were rather rushed. They had only 8 months to get them ready. So now Korolev took the next 2 years to improve the Molniya and the spacecraft as well. And the spacecraft was a brand new modular design with a standard cruise module and an interchangeable science module, and the other a probe for entry missions. And then you can see them here. The propulsion system is on the top. In 1962, 6 of these spacecraft were launched to Mars and Venus, 3 to Mars and 3 to Venus. And 5 of these 6 were victimized by their launch vehicle. And the only one that succeeded was Mars 1, the first spacecraft launched towards Mars, but it suffered attitude control problems and was lost after about 5 months of flight. Well, after his successes at impacting and imaging the moon from flyby, Korolev had stood down to develop these new planetary spacecraft that he launched in '62, and also at the same time to design a new lunar spacecraft for soft landing. This new lunar spacecraft was based primarily also on that 2MV planetary design. Had 2 modules at a cruise stage and then a detachable lunar lander. And these earlier Lunas, 1 through 3, flew direct trajectories from the 3-stage R-7. These spacecraft used the 4-stage R-7 and were injected from Earth orbit using the restartable 4th stage. These spacecraft had no solar panels. They were powered by battery because of the short flight time. And the 100-kilogram soft lander used airbags for terminal shock. Remember Pathfinder? In addition to the frustration, at the moon in '63 to '65, the Soviets were frustrated at Mars and Venus as well. So these lessons from Mars 1 forced a complete redesign of the 2MV. It became the 3MV, and worked to increase the reliability of the Molniya launch vehicle, particularly that troublesome 4th stage, which often did not ignite for the second burn. And so there were flight tests planned for this new spacecraft and the upgraded Molniya. These were the flights you see there in November '63 and February of '64, but these just revealed more problems. And the launch window crept up on the Soviets in the spring of '64, and so they just went ahead and launched to Venus. And you can see the results there. The Zond 1 was actually launched successfully, but it became clear right after launch that the spacecraft was not going to make it to its target. And so, in fact, it was called Zond 1 instead of Venera 2. And then later in the year, Zond 2 was launched to Mars. It was also recognized immediately after launch that it would not make its target. It was having difficulties as well, had multiple problems. And so then the Soviets decided to go back to a flight test to try to solve all these problems with the spacecraft. And so in 65, they launched Zond 3, not in a Mars window, but just to test the spacecraft to see if it could fly out to Mars distance and test all of its onboard capabilities during the flight past the moon. And it succeeded at that and became known actually as a lunar mission, when in fact it was a Mars test mission. But it survived after about 8 months, but didn't quite make it all the way out to Mars orbit. And then later in the year, they launched Veneris 2 and 3. Now these had some thermal problems, but they actually made it to their target. The first planetary spacecraft the Soviets launched actually made it to their target, but unfortunately, just as they were reaching their target, they failed. This was frustrating, very frustrating losses, but encouraging enough, because they got to their targets, that would lead to new attempts in the next opportunity. Well, at least for Venus. Well, Korolev's institution, OKB-1, was responsible for both human and for robotic spaceflight. But by 1965, when the Soviets had decided to compete with the US for a manned landing on the moon, they were fully occupied with the human spaceflight program. And Korolev realized he really could not do both. So he reluctantly transferred responsibility for the robotic lunar and planetary program to his friend, Georgy Babakin, and at NPO Lavochkin in late 1965. And Lavochkin modified OKB-1's lunar spacecraft and actually succeeded on the very first try, early in 1966, only days after Korolev's death. And although lagging at Venus and Mars, the Soviets once again had beaten the US to a space milestone, soft landing on the moon and sending pictures back. Luna 9 was the first soft landing on the moon, and it returned these panoramic images. Surveyor 1 followed in June 1966, and then in December that year, a second one, Luna 13, was sent to the moon by the Russians. Well, anxious to beat the Americans to lunar orbit as well, and that was announced by the Americans for mid-1966, the Soviets cobbled together an orbiter using their Luna 9-13 vehicle, replacing the lander with a pressurized module containing some readily available instruments. And after one launch failure in March of that year, they managed to succeed with Luna 10, which was the first lunar orbiter. And the U.S. followed that later on with Lunar Orbiter 1 and actually obtained the first images of the moon from lunar orbit, which was a sign that the U.S. was kind of beginning to catch up with the Soviets. The Soviets came up with an improved series beginning with Luna 11. The imager didn't work on Luna 11, but it did on Luna 12, and the series was quite successful in really mapping the lunar environment and obtaining data for the Soviets' manned program. They mapped lunar gravity. They actually discovered mass cons before the U.S. did, but they never published in time, and so the U.S. gets the credit for having discovered them. They measured radiation magnetic field activity around the moon and lunar environment. They imaged some cosmonaut landing areas, and they did some technology tests on board for the piloted program. Well, during the same time period as these new lunar successes, Lavochkin made significant improvement to Korolev's planetary spacecraft as well. For the Venus missions, they beefed up the probe to handle 18 atmospheres and a temperature of 400 degrees C. And they were rewarded with an immediate success, which is the first spacecraft to penetrate the Venusian atmosphere. Now, that was Venera 4, and it measured the composition of the lunar atmosphere, and it measured temperature, and it measured pressure during its descent through the atmosphere. But there was initial confusion over whether Venera 4 had actually reached the surface or not. Its signals ceased at a particular time, and the altimeter had not been operating properly. And later it became clear that it was really lost at an altitude of about 24 kilometers. But that controversy was not settled in time for the next window when they were launching Veneris 5 and 6. The probe was strengthened to about 25 bars, and they used smaller chutes to get through the atmosphere quicker for more rapid descent before the temperature in the probe got too high. So both were really not expected to get to the surface, and of course they didn't. They broke up at about 18 kilometers altitude. Well, while all this was going on at Venus and the Moon, Lavochkin decided, after they inherited the Mars program, to abandon the 3MV for Mars after so many failures. None have even come close, and adopted a new heavy spacecraft design that would be launched by this brand new powerful Proton rocket. And also Mariner 4 had by that time shown that the Martian atmosphere was exceedingly thin, which required a whole new type of lander than what they had been designing. And so what they came up with was a bold and new, demanding set of science objectives for Mars. And that was in 1969 to get the data they needed on the atmosphere to design a proper entry vehicle, and to get the ephemeris data on Mars. And then in 1969 they would upstage the U.S. mariners with a probe, and then in 71 they would upstage the American orbiters with a lander. They had a 3-year development challenge. This was diverted by all that work to be successful at Venus. And they used a brand new lunar spacecraft design that had been designed for the Proton. It was going to be used for the van program, actually. And then after having used that design, they decided that it wasn't really going to work all that well for Mars. And so they had to go back and redesign the spacecraft. They only had 13 months left to do that. They did it. Now, it was a big spacecraft. It was 3,500 kilogram orbiter and a 280 kilogram probe. And the probe was to be deployed from orbit in '69, but they had to delete the probe late in the development because it was getting into mass problems and it was not doing well in its tests, and so they replaced it with an orbital module. But as it turned out, both the Protons on these attempted launches exploded, actually very close to the ground, so U.S. monitoring didn't have time to figure out where these things were going to be headed because they exploded so close to the ground. Couldn't get any trajectory data on them. These were rather bold and, in hindsight, overwhelming objectives to try to attempt a soft lander after having no previous success on Mars, and only 33, and then finally 13 months to implement a new launcher. This was an enormous amount of risk, compelled by competition with the U.S. And the launch failures may have saved a lot of embarrassment. Those spacecraft were cobbled together pretty quickly. Well, while the U.S. closed in on a manned landing on the moon in 1969, the Soviet Union realized they were too far behind. There's another story behind all of that. I have no time to tell you. So they decided to counter with robotic missions to try to get a sample back before the Apollo 11 return. And they already had in development this new Proton-launched lunar spacecraft that I alluded to. And its purpose was to land a large rover to support their lunar cosmonaut program. And in an effort to upstage the U.S. Apollo 11, they just modified this vehicle with a sample return device by replacing the rover with the sample return avionics toroid, which you can see there, and a sampling device and a return vehicle. And they really were very clever in trajectory design. They used an ingenious return trajectory design that only worked for very specific spots on the moon, but its advantage was that with proper timing, it eliminated completely the need for any return navigation. You just fire straight up and you're guaranteed to come back to the Earth. No need for mid-course corrections or anything. Well, work began on this sample return modification in late 1968, just months before Apollo 11. And it's amazing that such a complex spacecraft could be so readily modified in so incredibly short a time. And it's really a testament to Russian culture, which is, hey, just do it. Dismiss all the hardship involved, use whatever is at hand, fix on the fly or fix during and after the build. And they made it work. One spacecraft failure was a launch in June, but later in July, Luna 15 actually reached lunar orbit and failed on July 13th during its attempt to land with the Apollo 11 astronauts still on the surface. 3 of these 11 sample return missions were successful, beginning with Luna 16. And 2 of the 3 rover missions were successful, beginning with Luna 17. And these are robotic achievements that have never been equaled in the U.S. Well, after their success with Luna 16 sample return and Luna 17 rover, the basic spacecraft was also modified for orbiters. The objectives were tied to the Lunar Cosmonaut program, mainly to obtain surface imaging at very high resolution, do altimetry measurements for topography, do remote measurements of surface composition and dielectric properties, do an accurate mapping of the lunar gravity field, and more environmental monitoring of radiation, plasma, and micrometeorites. Both were successful, but very few results were ever published. These were the last robotic elements of the Soviet program to land cosmonauts on the moon, which program was finally terminated in the mid-1970s. And attention turns back to the planets. And finally, in 1970, after 11 attempts in almost 10 years, Soviets achieved success at landing on the surface of Venus with the Venera 7 capsule. The Venera 7 capsule sacrificed a great deal of its payload and in order to beef it up to handle 180 bars and 540 degrees centigrade for 90 minutes. It was expected to fly through the atmosphere and land. They also used an even smaller parachute, to get to the surface quicker and maximize the amount of time on the surface. Unfortunately, that parachute failed, and it ripped first, and then it failed, and the capsule hit very hard, and the signal all but disappeared. You can see here where the parachute was deployed. This is the Doppler signal, where it was deployed, where it was unreefed, where it ripped, and then the swoop and oscillation as it streamed behind the spacecraft. Finally, it failed and separated completely, and the capsule free fell to the surface. You can see that little bit of signal in the noise that was on the surface. The Soviets didn't discover this until about a couple of months after landing. They thought it had crashed. And then somebody doing the data analysis discovered this 23 minutes of signal post-landing. And that probably happened because the capsule bounced and then tilted over, and the antenna was not pointing in the proper direction. So later on, buoyed by that, they sent Venera 8 to the twilight side. All these past probes have been sent to the dark side. Sent to the twilight side in order to fulfill the surface science objectives of this program and to get information on the light levels at the surface for later, more sophisticated landers with cameras. Venera 8 was a perfect success. They got profiles of temperature, pressure, wind, solar flux through the atmosphere. It identified the 3 cloud layers in the upper atmosphere, measured atmospheric composition, identified sulfuric acid in the clouds, and on the surface it found the 93 bars and 470 degrees centigrade. Well, next, back to Mars. And for the 1971 opportunity, the Soviets completely abandoned that Mars 69 design and had time enough to completely redesign the whole Mars spacecraft. This time it was a 3,400 kilogram orbiter with 1,200 kilogram entry vehicle and a 360 kilogram lander. They had failed to get the atmosphere and ephemeris data they really needed back in '69, but they did get the atmospheric data from Mariner 6 and 7 because these results were published in the open literature. And that allowed them to design the EDL system. But the U.S. would not release the ephemeris from the engineering data. This was back in the bad old Brezhnev days. So the Soviets decided on using 3 spacecraft, one of which was an early orbiter sent before the lander spacecraft, it would go into orbit around Mars and act as a beacon for the spacecraft that would follow. But they also, at the same time, incorporated a rather clever but very risky backup system using automatic onboard optical navigation at the planet to correct the trajectory and target the entry vehicles in case there was a failure. And it's a good thing they did that, because in fact, the Pathfinder orbital launch did fail. And so they had to rely on this automatic optical navigation system, which actually worked almost perfectly. This shows you the EDL sequence for the 1971 and also the 1973 missions which followed. The orbiter was targeted for the Mars orbit insertion point on approach, which meant that the EDL system required propulsion in order to target to the proper entry point. The EDL package was deployed at about -6 hours. A solid rocket was fired to target the vehicle to its entry point. Then that system was ejected. The spacecraft was oriented towards the proper entry angle and then spun up with little small solid rockets. And after peak deceleration at about 2 Gs, it was spun back down again. And then the descent sequence was triggered after reaching about Mach 3.5 with a pilot chute and a drogue chute and a reefed main. And after that, the lander was exposed. The main was unreefed. And then when it got near the surface at about 20 meters altitude, about 10 meters per second velocity, the retro rockets were fired and the lander was dropped. As far as how this mission went, for the landers, Mars 2 was unfortunately improperly targeted on a steep entry angle and crashed. But Mars 3 landed successfully. It turned on its transmitter about 90 seconds after landing, and then transmitted about 20 seconds worth of data, which turns out to be mostly noise, and then died. The orbiters also had telemetry and camera problems, and they had a dust storm to deal with, and so little data was obtained from Mars 2, but from Mars 3, about 60 images were obtained, and it got new data on the atmosphere, on surface properties, gravity, and the orbital environment of Mars. Well, at the next Mars opportunity, the Soviets were aware of plans for Viking, and they were rather chagrined by the Mariner 9 success relative to their 1971 fleet. And so they were determined to beat the U.S. to the surface in 1973. 73 turned out to be a period of detente. And so data from Mars 2, 3, and Venera 8 were exchanged with the U.S. For the ephemeris, atmospheric models of the planet, and Mariner 9 imagery of potential landing sites. But this 1973 fleet was doomed to a fatal error. The Mars 73 electronics substituted a new aluminum lead transistor for the 1971 gold lead transistor. And this was used throughout the spacecraft, very common transistor. And they only discovered a few months before launch that these actually had a very short lifetime to failure, on the order of the flight time of the spacecraft. And it was just simply too late for substitution. It was used throughout the spacecraft. And the 50% calculated failure rate would have dictated postponement in the U.S. And the Soviet engineers argued for delay, but in a rush to beat the U.S. to the surface, the Soviet Soviet decision makers simply decided to go ahead. They used 4 protons. They launched 2 5-ton orbiters and 2 5-ton flyby landers with these transistors in them. And all 4 of these spacecraft experienced serious failures en route to Mars and at Mars due to this transistor. Mars 4 had serious computer problems. It could not make its second mid-course correction, and the engine failed to fire to put it into a big, long looping orbit, and it flew past the planet, taking a few pictures. Mars 5 actually achieved orbit, but the Mars orbit insertion event triggered a pressurization leak, and it failed after 14 days. Now, that meant that there were no orbiters at Mars to do relays of data that would come from the subsequent landers. And the best they could do was to get data from these landers during the flyby, from the flyby spacecraft that dropped them during a short period after landing. Well, Mars 6, after it conducted its first mid-course, its downlink failed. So the Russians could get no data from the spacecraft. So they uplinked in the blind, hoping it would work. The spacecraft automatically determined its course and made its corrections. And then when it got to the planet, it did the optical navigation, did the entry system retargeting, and all of that was successful. And the first time the Soviets knew the spacecraft was still there was when they started to get the data stream from the descending vehicle through the flyby spacecraft. Absolutely amazing. It was a monumental achievement in autonomy, but the lander lost signal just as it was dropped to the surface. Mars 7, they deployed the entry system, but it did not fire, and so it simply missed the planet. The Soviets got some temperature and pressure and Doppler data from the Mars 6 descent. They got some data from the Mars 5 orbiter on the ionosphere, the atmosphere, something on the surface, and some imagery, but little result for such a massive investment. Well, later years turned out to be much better for the Soviets, and this was probably their golden age. And they had great success with their subsequent Venera program, Veneras 9 and 16, these big sophisticated landers on Mars. And probably the pinnacle of the Soviet program were the Vega missions, about which I don't have any time to tell you, in the mid-1980s, and then failure revisited them again with the failure of the Phobos missions, and finally the 1996 loss of Mars 96, which was simply a humiliating final to the Soviet venture in robotic exploration. Well, the Soviet program is really kind of a tragic loss of vision and enterprise and expertise. These folks just disappeared after Mars 96 for a long time. They had the courage and enthusiasm to try things that were really considered rather difficult to do and almost impossible. They had a superb expertise in engineering, design, and development, terrific engineers. They used a great deal of innovation, using technology that was available in order to accomplish the task at hand. They were masters of material development and engineering. Their propulsion systems are unmatched. They showed a lot of excellence in celestial mechanics, and navigation, and guidance. And they showed excellence in automation and software, which rather unraveled later on in their program. But they did produce a stable of very powerful and readily available rockets. And they're really done in by the poor reliability of these launch vehicles early in their history until about the mid-70s. And they became very much better. They were handicapped by a rather poor electronics technology. All of their flight vehicles were pressurized. They had a weak system engineering discipline, and they rather had poor buildings and things for ground system testing. They didn't do sufficient ground system testing, and probably the worst was this very complex, this entangled and heavy-handed national system they had for control and supply. But in the early years, in spite of all of this, after 15 years of the program, they achieved a very large number of firsts. And among them, they were the first on the moon, they were first on Venus, they were actually first on Mars. And now I'd like to bring up Mikhail.
Good morning. First of all, let me say that I'm very much pleased to be here. Appreciate the invitation to take part in this symposium. And also, I would like to appreciate the joint efforts we are undertaking jointly with Wes in order just to write a book on Soviet robots. Because it's the first time in the history, it's absolutely objectively reflect the situation in the former Soviet Union, and it's allowed us to consider and to view the problems from the different viewpoints, but in very accurate and very realistic historical retrospective. Well, Wes perfectly reported the main issues of this book and very proper description of the situation that we had throughout the first several decades of space era. And well, I've been a part of this process throughout the years, beginning of the first lunar missions, so I witnessed the situation just sitting inside. And well, I wouldn't like just to leave you with the impression that everything is already over, that we completely, just finished our efforts. And I will try to complement a little bit the talk Wes gave to you, and to tell about the current situation in the current Russia, and just to give a few actually principal items to tell about some new ideas and the process which currently keep going in the country. Okay, so certainly disintegration in the Soviet Union badly impacted on the situation in the country, and it was followed by social economical turmoil, upheaval, and well, actually badly impacted on the space program, specifically on the planetary exploration. Well, space budget was shrank dramatically. For nearly 10 years, we had very poor governmental supply, and space facilities were probably destroyed. Many people lose the people, and cooperative links broken. Skilled personnel in space science and technology lost. It was really awful situation in the country. And Mars 96, it was prepared at such very poor background, It was actually, I've been in the facilities in the Lavochkin enterprise. It was assembled by the partially hungry people. So we couldn't expect that it will be success, and this so happened. Mars 96, in which participated 22 countries, failed. And well, it was great disaster, and really, again, very badly impacted on the planetary program. Well, but initially, it looks like no return back, no chance to return back. But I will try to tell you that the situation right now much more optimistic, and that's why I am quoting at the upper part, the quoting from the famous American author Mark Twain. Rumors about my death are too exaggerated. That is the situation to us right now. So, after Mars 96 loss, we decided to completely renovate the basic idea for the planetary missions. And it was originally a group of several enthusiastic people. We work for nothing. I just reported at the first idea about the new concept of the planetary spacecraft in one of the meetings at the end of 90s. And some good colleagues of mine addressed me and said, well, okay, you are working, not being paid. You are either romantic or completely stupid. I said both. Okay, anyway, it was completely new approach, and it was essentially the basic spacecraft which underlined the Phobos ground mission. We targeted just to return back to the poorly implemented Phobos 88 mission with the completely new spacecraft. And it's shown the main concept, I mean the spacecraft profile, spacecraft profile and the mission flight toward Mars and Phobos, and these sketches. Well, unfortunately, because insufficient finding, the mission postponed 3 times. Originally, it was scheduled for 2004, but actually, it was launched in 2011. We very much relied on this mission, and I personally worked on the mission for about 15 years. And when it failed and couldn't leave the LEO orbit, it was like it's a personal tragedy to myself even. Basically, the failure was caused by the factors rooted in the destroying 90s in our planetary program. That is some kind of the harvesting, just what we had with the Phobos ground mission. Okay, as I said, not so bad everything right now. I will try to get you acquainted with the principal steps forward we are right now undertaking, and this is Russian space program on science generally. But this is bottom band. It's just missions for the solar sun exploration and astrophysical mission. I will not comment it. Also, you should be aware that, okay, that is as of middle of 2011. And right now, it's already modified because the time changed very fast. Anyway, Phobos soil. Phobos soil was failed, as I said. Right now, excuse me, we focused on the moon exploration. And in the moon exploration, we just plan to launch in the coming years 3 missions. First one is the lunar globe, but here it's shown only one spacecraft because it's originally thought to be just an assembly, both orbiter and lander. Right now, we launch in 2015 lunar globe lander, followed by lunar globe orbiter in 2016. Lunar resource, it's more large scale. It's, well, the very small rover, which will be complemented and just joined to the spacecraft by the request of the Indian side, because the Indians participated originally in this program. And even we intended to launch lunar resource on the Indian launcher. But they encountered some problems with testing of their stage, second stage engine, and right now it decided that we will do it by our own. So for lunar program for the coming year, we have 3 launchers already committed, and I think this program will be implemented. Well, next it's the Venera D, but Venera D, it was scheduled originally for 2016, but right now it's postponed after 2020, something like, I guess, to 23, 25. Also, it's at MarsNet, but MarsNet, it was original concept. This is a sort of the small vehicles judiciously distributed over the surface and controlled by the flying computer, actually. Very wise, very nice concept. And right now, it's also canceled because after Americans stepped down from the program ExoMars, which were invited by the Europeans, the doors became open and we entered the doors. And right now, this already agreement exists, committed with the Europeans, and it looks like ExoMars, not MarsNet, will be implemented in the 2 phases. First phase, 2016, it will be orbiter, and 2018, it will be rover on the Mars surface. And finally, not finally, actually the lunar program will be followed by it's already in the blueprint, this will be followed by the 2 missions, very capable lunar rover with the capable manipulator in order to pick up different samples, and then with the return rocket will be landed just beside this rover. Well, both lunar globe, lunar resource, and also the follow-up missions are targeted to be landed in the South Pole in order, with the main idea, beginning of the lunar globe, just to study volatiles and first of all the water deposits in this soil. Okay, and finally, we are going also to continue our efforts for the Mars exploration, and in our blueprint, Mars sample return is scheduled for 2022. I hope it will be possible to do. Well, let me conclude with the very nice quoting from the American good publisher, writer, David Harland, who just published his comment on our Wes and my book on Soviet robots, and I don't need just to read it, but just only to ask to draw your attention that it was demonstrated that planetary scientists and engineers in the Soviet Union, Russia, have been working with minimal resources, poor political support, and less than optimal technologies many years. And in the conclusion, that Phobos Grund must be viewed as part of long train of missions over the years. I hope it is not the last such missions undertaken. Just what I try to show you and try to persuade you, actually. Actually, let me also repeat, like Mark Twain, rumors about our death, about that planetary program in modern Russia, too much exaggerated. Thank you.
We are running over, but the next panel, we're short of paper, so we're going to run just a little bit. Let's take about 3 questions. How about, Wes, would you like to come up? Start over there with Jim.
This question is directed to Mikhail. As you correctly pointed out, the United States had changed its approach now with Mars and backed off its agreement with ESA for the 16 trace gas orbiter and the 18 ExoMars rover lander. As you also mentioned, the aspects of that now are allowing Russia to make a more solid agreement with ESA. how is that helping raise the cost and expertise in attracting new engineers and into the Russian program? Is that helping?
Oh, thank you. Well, according to the agreement we signed, I mean, Russian head of the Russian Space Agency, Popovkin, and the head of ESA, it was just completely, you know, single efforts. It was not specifically committed to make something jointly, okay? It will be different component which we assemble in the mission, okay? And, well, I could complement also, I do not envisage that it will be some kind of the additional support for example, in terms of the Western technology invested in the program. No, we will be doing this by our own. Well, okay. Thank you, Wes. Well, you know, certainly the more joint efforts will be in the area of the bringing people together. But this already, you know, just a good experience we're having throughout the years, because, you know, our specialists, first of all, our scientists, working together with Americans and with Europeans. And for example, Venus Express and Mars Express and Venus Express missions, they are just, you know, equipped with something like possibly 50% of the Russian instruments. And engineering also doing very closely together.
Hi, great talk. You know, we've heard a lot here yesterday about the political support for the American program. And I'm curious about the process on the Soviet side by which all these missions were proposed and approved, and whether you could talk a little bit about the process. Who were the decision makers? Who were the people who needed to be persuaded to support these things? Presumably the role of the Ministry of General Machine Building, but also perhaps the Central Committee. What are the roles of, you know, the Institute of Space Research, the Academy of Sciences? How much support did the Korolev and Lavochkin design bureaus enjoy? How did that support rise and fall over time through the Soviet period at least? And right, yeah. So why don't I stop there?
Well, Mikhail knows a lot more about this than I do.
Yeah.
And he helped me a lot to write about the exact same things in the book. So it's a long story. It's a complicated story. And so it would take us 15 minutes to answer all that. But read the book. It's all in there.
All right.
Well, I could only add, you know, in the former years, which Wes told you about, we had no lacking with the financial support, because it was Cold War motivation, you know. Like a project scientist, let me say I've been showered money. If it was some kind of lacking, I just addressed to the decision makers and said, okay, Americans will beat us. It was great motivation. But not right now. And right now the situation dramatically changed. And we will be completely lacking of resources throughout the 20 years. Right now, the situation very, very positively changed, and we have quite sufficient support.
First of all, that was a really fascinating joint presentation by both of you, and I thank you both for both for your efforts and sharing all this interesting information and perspective with us. In hearing all this, one is struck again by the great contrast in the Soviet successes at Venus compared to the record at Mars. And especially hearing these details, the history with Mars is really a sequence of kind of heartbreaking near misses and almost successes. And I wonder, my question is about your perspective on that contrast between the record of success at Venus and the record of not so much success at Mars. And we've heard a lot of details about how all these Mars missions could have worked and almost worked, but my question is, beyond just the sort of series of unfortunate events, is there some more profound explanation that you have for this great contrast?
Well, first of all, it's the great galactic goal. But,
Well, you know, David, in the years, we several times failed. It was some kind even of, you know, very, very, I would say not scientific concept, but somebody sitting on Mars preventing us to have success, okay? Unlike for Venus. Well, but we certainly, and I showed you in my slides, to us, it was really great lessons learned. And we very profoundly analyzed that everything which happened with us. Specifically, we are trying to undertake new Mars mission, okay? And it's also specifically concerns Phobos ground loss. Because, you know, as I said, it's rooted in our former, you know, lacking in both in technology, absolutely absolutely agree with Wes that it was first of all electronics, okay, and the avionics actually. But we reanalyzed it, and the new approach for the mission is completely different, also in the managerial area. Okay?
I think that was one of the most amazing presentations I've seen in a long time. Join me in thanking our and we will trim 15 minutes out of. Let's take a break and be back here at 1:45 for the next panel.